Now we're going to talk about black hole thermodynamics. Uh, the no-hair theorem suggests that the black hole, being characterized only by mass and spin and charge, are extraordinarily simple entities. One may wonder because since it's so already simple, black hole has vanishing entropy. Uh, if interesting that you right away you will lead to the contradiction. The process matter falling into black hole would then be an entropy decreasing process. Okay. So at the end of the 1960s, uh, Bekenstein was a student of Wheeler at Princeton, wrote a thesis to point out that the black hole must have non-vanishing entropy and suggests that this entropy is proportional to the horizon area. So black hole is somehow proportional to the area of the entropy of the black hole is proportional to the area of the black hole. So let's talk about black hole area. So if we talk about a simple case of a Schwarzschild black hole, so the area we're talking about, the area of the event horizon sphere, which the area is a star equal to 4 pi r star squared, just like a usual spherical surface, and they plug in the expression for uh, Schwarzschild radius, you get this expression relating the area to the mass square of the black hole. Proportional constant was Newton's constant c things. Okay. Now if that's the case, when a matter falls into the black hole, the area, and if the proportion to entropy, as Bekenstein suggests, will be ever increasing because which means that the initial area must be less than the final area. The reason is because the initial area is the some area for the black hole plus of the mass falling into the black hole has area. So therefore, there's two black hole areas is of course less than the final black hole, which would be the energy conservation be m plus dm square. So therefore, the area must ever increasing. So this area or entropy increasing theorem will imply that two black holes can join to make a bigger black hole, but one black hole can never split to two because if in order, a black hole's mass two parts, and the two parts break into two black holes, the area would be the initial area would be this, and this is the final area, but the final area would be obviously less than this, so therefore it's not greater than the initial area, which would violate the theorem. So therefore, it can never happen. And also going to talk about some laws of black hole mechanics. An example, one example says the changing of black hole mass is proportional to the changing its area, and the proportion constant is given by the surface gravity of black hole. The surface gravity is Newton constant mass black hole divided by the Schwarzschild radius squared. And well, that's because just remember the surface gravity on Earth is the mass Earth times Newton constant divided by the radius, exactly the same. By this analogy, you can write down the surface gravity of black hole, which you plug in the expression for uh, Schwarzschild radius gives this expression. Now we can easily derive this relation by differentiate the area of the area expressed in terms black hole mass in this relation. You differentiate, and of course you pick up by 2, so 16 becomes 32, and MDM. Okay, now because this coefficient can be expressed in terms of the uh, uh, black hole surface gravity because you have GM, so the GM factor and left was G and divided by the surface gravity. So therefore, the change in mass of a black hole is proportional to change in the area, and the proportion constant is surface gravity divided by Newton's constant. So that's an example of laws of black hole mechanics. Now, of course, it didn't say anything about the proportionality of area to entropy. So, in fact, this is the derivation. I just point out the steps. You substitute this in, differentiate, and then substitute to the surface gravity expression. Now, the proportionality between area and entropy is actually part of the mysterious correspondence between laws of black hole mechanics and thermodynamics. It's not only this, you will see them, which we're going to talk about. So there's a deep analogy between laws of mechanics and thermodynamics. So first, let's talk about laws of black hole mechanics. We can see the four laws. The zeros law says the surface gravity has the same value everywhere on the event horizon. Okay. And this first law says the change in mass of the black hole is proportional to the change in surface gravity to the surface gravity times the change in area. It's the one we just talked about last slides. Okay, Tm is proportional to A. The proportional constant is the surface gravity. And the surface area of event horizon black hole can only increase, never decrease, which we already talked about also in the last slides. It's impossible to lower the surface gravity to zero through any physical process. Okay. Now, compare this to the four laws of thermodynamics. Zero's law says the temperature of a system in thermal equilibrium has the same value everywhere in the system. And the first law of thermodynamics says the change in energy of a system is proportional to its temperature times the change in entropy, D equal T times Ts. The second law, the entropy of a system can only increase, never decrease. And it's impossible to lower the temperature of a system to zero through any physical process. Okay. So you can see here the surface gravity is replaced by temperature. Here Tm is replaced by energy, and the Ta is replaced by entropy, and surface gravity again replaced by temperature, and the area increasing and the entropy increasing the same. Okay. So therefore, there seems a mysterious analogy between the law of mechanics and the thermodynamics was mass in black hole replaced by energy of the system. The surface gravity of black hole is replaced by the temperature of the thermodynamic system, and the area of a black hole event horizon is replaced by entropy. Okay. And so really all says that these two set laws look analogous. So always say they may be proportional to each other, but of course, temperature proportional to surface gravity, entropy is proportional to area. Of course, we have no idea what the proportion constant is and why. So in the next lecture, we're going to talk about Hawking radiation, in particular, talk about quantum fluctuation around the horizon. And then the proportion constant between temperature and the black hole surface gravity and entropy and area will be obtained. Okay, and then give us a glimpse of the statistical glimpse of the quantum gravity.